So this related rates problem number 5 here is about a balloon that's going up, a person that's got a line of sight watching it, and we want to know, so what's it going up at, 10 feet per second, so it's rising, what seems like pretty quick. Person's 100 feet from where it took off. The balloon is 50 feet off the line of sight, really, is the way that I'm going to do this one. So off that line from where their eyes are. It's not to scale. If this is 100 feet and that's 50 feet, then it's clearly not to scale. But we want to know is at what rate is this angle changing? So what we're going to do is set up some triangles, and we're going to have a theta in it. Usually when we have theta, we use SOHCAHTOA. So we'll see which one works best. So we're going to start with drawing that triangle. I'm going to draw it a little bit more to scale this time. Theta, 50. I'm going to call this y because I know it's going up. Maybe what I'll write is 50 equals y. And I'll write dy over dt is equal to, how fast is it going up? 10 feet per second. Okay, so, and I also know that this is 100. I'm not giving that a variable in this case because it's not changing. So let's see what we can do to start setting this up. I'm going to go and actually, so here, what are we using? This is an angle. This is opposite. This is adjacent. I could use Pythag to figure out the hypotenuse, but this is a good number, nice, easy number. And I already know it. It's less work to not have to find that yet. And tan actually works well, and you'll see that. So I'm going to write tan of theta is equal to opposite, which is y, over adjacent, which is 100. You may say, dude, why didn't you put 50 there? Because I know y is 50. Well, remember, whenever we do one of these related rate problems, we always need variables for things that are changing when we do our equation. So, and since y is changing, I can't just use 50. So let's d over dt this. That gives me secant squared of theta. Whew, that's a derivative. Times the derivative of the innards. That would be a d theta over dt equals, all right, you may say, I don't want to use quotient rule. Well, you don't have to use quotient rule because this right here is this is a coefficient. So I get dy over dt all over 100. I think you can see why I wrote the dy over dt like that. All right, so from here, I am going to divide by secant squared theta. I'm going to do it a little different order than the other ones. Remember, I'm looking for d theta dt. So I'm going to divide by secant squared so that it is on that side and I have the d theta dt isolated. That gives me d theta over dt equals dy over dt over 100 times 1 over secant squared of theta. Secant is hypotenuse over adjacent. You should know that. And so 1 over secant is going to be this flipped upside down. What's that? Adjacent over hypotenuse when I flip these two. So what I can do is I can rewrite this as d theta over dt equals dy over dt all over 100 times cosine squared of theta. So we know some things here. The first of which is that we know dy over dt. If you look at it, I don't think I did it. Dy over dt is 10 feet per second. So I'm going to take this right here, slide it in right there. And I'll write that, I guess I'll write equals, I got my blue, 10, and then over 100 times. Now, I need to figure out what cosine squared is. So in order to figure out what cosine squared is, I'm going to start by figuring out what cosine of theta is, and then I could just square that number. So if you think about cosine of theta is adjacent over hypotenuse. So here's my theta, here's my opposite, here's my adjacent, here's my hypotenuse. I need to go and find the hypotenuse of this right triangle. There's a right angle right there, in order to find the cosine. So what am I going to use? I'm going to use Pythagorean theorem. And at this point, I have already taken the derivative, so I can go ahead and plug in that y equals 50. I can use that 50. So what do we get? I get that, let's see, h squared is equal to 50 squared plus 100 squared, which gives me h equals the square root of, when I do that, I wind up getting 125,000. That's 50 squared plus 100 squared. All right, so what is cosine of theta? It is adjacent over hypotenuse, which adjacent is 100, and then hypotenuse is this messy root, and you'll see why I'm leaving this. What do I get? 1, 2, oh, you know what? I had an extra 0 there. I'm going to go back and erase this and fix my comma. I'll just erase this whole thing. What do I have? 12500, not with an extra 0 there. So 12500. All right, so from there, I want to find cosine squared. So I'm going to write cosine squared of theta is equal to, well, that's just 100 squared over the bottom squared. Well, the bottom has a square root, so what do I get when I square that? I get 12500. The square root just goes away, which I can write that as 100 and then add 2 more zeros and then divide it by that number, the 12500. And look, a bunch of things cancel, and I get 100 over 125. Now, that simplifies more, but I'm just going to roll with that as is. And that is going to replace this because it's a cosine squared. So I'm going to get 100 over 125. So what happens from here? This cancels with that. I just get 10 over 125. And then, so 2 ways to write that. We could write that as 2 over 25, or we could just give it as a decimal, which seems totally reasonable here, 0.08. Now, the units for this thing is a little complicated, and I will very, very briefly talk about it. It is in radians per second. And that's just because that's the way the calculus works, because when we do our calculus, we work in radians, and we don't work in degrees. And that's a whole nother discussion that I'm not going to get into. For me, my test, I'm not super concerned with the units that you use, but for this one in particular. But the answer for this one is that the rate of change that this angle is going up is 0.08 radians per second.